completeness, but also of continuous dependence on the initial condition, existence of a flow or semiflow in case there is an infinite number of driving Brownian motions, or we have Cognita-type noise, and also if we replace global Lipschitz conditions by local one-sided Lipschitz conditions. So the setup will be the following. So we consider now a stochastic differential equation on RD of Cognita type, and I'm not assuming that everybody is familiar with this, so I'll introduce this. So assume that the drift function is continuous, and that M is a continuous martingale field. Now, continuous martingale field means that for every x in RD, we have a martingale, continuous martingale starting at time 0, and these are somehow correlated, and the correlations are given by this joint quadratic variation. So we assume that at different locations, x and y, these martingales have a certain quadratic variation, which is differentiable in t. The derivative is actually a function which is assumed to be continuous, deterministic, and time independent, just for simplicity. And then we define this calligraphic A in this way, and a good way of thinking about this is to take the difference of martingales at locations x and y, take the derivative of the quadratic variation of that one, and that's what this means. I will tell you in a minute what these quantities are like in the classical case, where we have just a finite number of driving Brownian motions, and then we assume throughout the talk that we'll have this one-sided local Lipschitz condition. So twice, and this denotes the standard inner product on RD, so twice the difference of the drift at x and y with this one here, and the trace of A of this matrix is bounded up by kn times x minus y squared, where this is the standard Euclidean norm on RD. What this means is just for every n, there exists some deterministic number kn, which can increase to infinity as quickly as you wish, such that for all x and y inside a ball of radius n, this property holds. Okay, and then I'm claiming that the stochastic differential equation up there has a unique local strong solution. And even in this setup, this does not seem to have been proved in the literature, even though essentially it has, namely under the condition where this driving field is actually generated by just a finite number of Brownian motions, as I will tell you in a minute. But before doing so, let me translate everything in the classical case. In the classical case, which was the one on the first transparency, where you just have a drift and a finite number, so sum of sigma j of x dwj. In that case, these martingale fields are just given by this thing here, and the matrix calligraphic A given here has this form, and the trace of that matrix is just this one here, as you know. So this is then the usual one-sided Lipschitz condition, or local Lipschitz condition here. Okay, I'd like to show you the idea of the proof, not mainly because it's completely new. It very much follows the traditional way of proving the theorem in case you just have a finite number of Brownian motions. But first of all, it gives me the chance of introducing some of the meaning of this equation, what it means for a process to be the solution of this, on the one hand, and also it gives me the chance of advertising a lemma which actually provides a shortcut in the usual proof of the theorem. Okay, so here is the idea of the proof. So it goes back to Krylov in a paper from 1999, I think, and the proof has been worked out in the book by Prévost and Röckner, which appeared in 2007. This is the idea of the proof. So you take an Euler approximation. So you take some fixed initial condition with x in RD, and then you freeze the initial condition for time 1 over n. You plug it into here, so you just take the martingale, which is sitting at this particular location, and just take the increment of that martingale over a time interval of length 1 over n. And here you also freeze the initial condition, and then you update after time 1 over n, and then you plug it in again and iterate. So this is a good way of actually thinking of a solution, namely to take this Euler approximation. So this martingale field just tells you about the increments or the local infinitesimal push which your solution gets if you're at this particular location. Okay, now of course you try to show that this Euler approximation converges, so you want to show that this is actually a Cauchy sequence in some appropriate space, some appropriate complete space, and then try to show that the process converges to actually solve the original equation. Okay, so how do you do this? Well, you take the difference between two approximations, you square, you apply Ito's formula just as usual, and then this local Lipschitz condition comes very handy. Maybe I'll just write it here again. So this condition is 2 times p of x minus p of y in a product with x minus y plus the trace of the matrix A x y is more or equal to kn times x minus y square. And this is true for all x and y norm at most n. Okay, so when you apply Ito's formula to this, what you get, at least, I mean, you have to stop, do this only up to an appropriate stopping time, and then if you apply Ito's formula, you see that this comes very handy because you just use this estimate here, which gives you this one here. And then you end up with something small, which comes from the discretization here, which I don't want to specify. And then you have an additional local martingale NT, continuous local martingale static at 0. Now the question is how to continue. You want to show this, this is really a Cauchy sequence. So you have to show that this is somehow small, very small, when n and m are large. How do you do this? Well, in the classical case where you have Lipschitz conditions, you would proceed as follows. You take the supremum here over little t from 0 to capital T, say, take the expected value, and apply Burkhalter's inequality here. And then Burkhalter's inequality transforms the soup into a quadratic variation term, which you then estimate by the Lipschitz condition, and then you apply the usual Cronval lemma, and basically you're done. You've shown that this is a Cauchy sequence. Now here you cannot do this. Why not? I mean, you can apply Burkhalter's inequality here, but we don't have a Lipschitz condition on the noise. We just have this condition, and it may well be that this is not at all Lipschitz, not even locally Lipschitz, so this doesn't help here. So you somehow have to think of a different way of proving that this is small if this is small, without having any control of the quadratic variation of this local martingale. And, well, this has been done in the literature, but here is a lemma which actually does this for you. So that's the lemma I want to advertise here. So it's a lemma jointly with Max von Renesse, which we proved and used in a paper dealing with stochastic delay equations. I'm not claiming that this is new, but so if you have seen this before, please tell me, but I haven't seen it in the literature. It's anyway not difficult. So the assumption is the following. You have some non-negative adaptive process which satisfies this inequality here. N is a continuous local martingale starting off at 0, K is some deterministic constant, say, and H is some adaptive process. And then the aim is to deduce from this inequality some bounds on the soup of the Z process which do not somehow depend on the local martingale, but which somehow are independent of the local martingale. And this is a possibility of doing this. So for each P which is strictly smaller than 1, and that's important, and for any alpha which is somehow bounded below by this number, there exists two constants depending on P and on alpha, such that the soup, so the star stands for the running soup, just like here, the Pth moment can be estimated in this way. This is not hard to prove. It's even easier to prove if you don't have this soup in here, then it's almost just 5 or 6 lines. With the soup it's maybe 10 lines. And once you have this, then you're basically done, because you see this has exactly the form of this one here, provided at least this something small is so this is somehow covered by this H here. So if you can show that this is really small in the sense that this converges to 0 here as n and m go to infinity, which you can, then you're in business, and then you see that this will actually be a Cauchy sequence in this corresponding space here. Now, so you don't need to do anything in addition. So this proves that this is a Cauchy sequence. It's a complete space, so you do have a limit, and then the rest is as usual. You have to, I mean, this is just locally, so you have to delocalize and so on, and also uniqueness is shown in the same way as usual. Okay, so this shows existence of a local solution. Of course, it may explode. No linear growth condition or so. So far, we can just show existence up to some explosion time. Okay. Now, what about global solutions? So for global solutions, we need something like linear growth condition on the coefficients, and this is what one can prove. It's actually slightly weaker than a linear growth condition, so it's a kind of generalized linear growth condition in the sense that the sum of these two terms, they don't actually have to satisfy a linear bound. It can be slightly larger than linear, but this integral should be divergent, so something like x log x or so is okay. That again is very easy to see. Okay, again you apply Ito's formula to the square. So far we only know that we have local solutions. They may explode, but as long as you take some time which is strictly smaller than the explosion time, then you can apply Ito's formula. You get this term in here, and then you can estimate this simply by this term here. So you get this, and you see you again get an inequality which is somewhat similar to the one which we had in the lemma before, except that this is now nonlinear rather than linear. And again, n is a continuous local martingale. We don't have any nice control on the quadratic variation of that one, so we would like to get somehow deduce from this that the process X will actually not explode. And there's again a lemma in the same paper which comes to our help here. So if we have an inequality like this one given here, so Z is an adapted continuous process, possibly just defined up to some stopping time sigma, n is a continuous local martingale, starting off at 0, c is some constant, and assume that we have this inequality up to the stopping time sigma. Then if the sigma is maximal in the sense that the sup of the process Z really converges to plus infinity as t approaches sigma, on the set where sigma is finite, then sigma is actually infinite almost surely, so this solution will exist globally. Okay? That's all you need, and this is also easy to prove. So you see the whole thing is actually quite easy to prove. So much for existence and uniqueness of solutions, but now I want to address the question of continuous dependence on initial conditions and existence of flows, semiflows, and so on. So one of the questions you can ask is whether these conditions written here up to here, so this local Lipschitz condition and the linear growth condition, whether they will actually allow for continuous dependence on the initial condition. So let's see to what extent this is true. So this is the question. Are our conditions, that is this condition, the condition here, plus the generalized linear growth condition, are these sufficient to guarantee existence of continuously dependent modification, continuous depends on the initial condition, or even the semiflow property, which I'll introduce in a minute. And in particular, the question is if these conditions are satisfied, which we had up to now, so linear growth condition plus this one here, does that imply that there exists a modification of the solution which really is RD valued, so it should not explode, and which is jointly continuous in both variables? And that's what we mean by strong completeness. So just the existence of global solutions, maybe I should go back. Didn't say this, but it's in here. So sometimes people call existence of global solutions just completeness, weak completeness or completeness, as opposed to strong completeness, which means that there is a continuous version taking values in RD, and that's an important difference. These concepts do not coincide at all. And so the answer to this second question is a clear no. And I'll show you an example. So actually, there exists an example of a two-dimensional stochastic differential equation, even without any drift, just driven by a single Brownian motion, and with bounded and C infinity coefficient, which is not strongly complete. And there is an example in a joint paper with Shumei Lee, which appeared last year. And let me just remind you or tell you, depending on whether you've seen this before or not, of the example. I just briefly try to indicate the idea of such an example. So it's a two-dimensional STE, and let me denote the first component by x and the second one by y. So this is a two-dimensional STE, no drift, and we assume that there's no motion at all in the y direction, and there's no drift. So we just have a diffusion sigma and as a dWt here. So one-dimensional Brownian motion, and I'm claiming that you can choose sigma in such a way that it's C infinity and bounded. Actually, it's even bounded by 1 from below and by 2 from above. So it just varies between 1 and 2, and you can choose it in such a way that this equation is not strongly complete. It's certainly weakly complete because sigma is C infinity. So sigma is C infinity, therefore, of course, locally Lipschitz, and it satisfies the linear growth condition, of course. So certainly solutions exist for every initial condition, but I'm claiming that you don't have a continuous global modification of the solution. So the idea is the following. So say this is y, second component, this is the first component. So if you look at this, you see that if you start somewhere here, so if this is the initial condition, then there's no motion in the y direction, you just move in the x direction, and it's basically a Brownian motion up to a sigma, which is between 1 and 2. So in this direction, you just have a Brownian motion. Okay, so of course this doesn't explode in finite time. But I'm claiming now you can choose the sigma in such a way that, for example, if you start with a whole set and whole interval of initial conditions, then this thing will blow up in finite time, even though each fixed point on that will not blow up, but there will exist points which will blow up in finite time. And the way you can do this is, you can first of all think of the following case, namely if for different values of y, you get a Brownian motion which was independent. So this was a Brownian motion, and this was also a Brownian motion, and these were independent for different values of y, which is of course not possible here. But if that was the case, then of course you had infinitely many Brownian motions, independent ones, and then of course some would run away just immediately because there are infinitely many. Now you cannot do this here because sigma is locally Lipschitz, it's even C infinity, and we just have one Brownian motion, but you can somehow mimic this kind of behavior by letting sigma change very rapidly. The further out you go, the sigma moves very rapidly and with a different frequency here, and then somehow you can imitate this behavior, and so the larger x is, the more independent solutions look if they have a different y component, and that you can somehow do in such a way that this whole thing will actually take off in finite time. Okay, that's the idea of this example, and so now we are looking for positive results guaranteeing that this will not happen. So that's an example which is not strongly complete, but it is weakly complete, because for every fixed initial condition you do have a global solution. Okay, so there's a lemma here. Assume that we have this kind of one-sided Lipschitz condition. Now it's really a global Lipschitz condition, so this is a fixed number k, not depending on n. But now we have an additional term here which did not appear here. So to get continuous dependence, we need a slightly stronger condition, namely some mu in front of here, and this is the usual matrix norm, which, since this matrix is positive semi-definite, it's just the largest eigenvalue of the matrix. Okay, first of all, if you have this condition, then the SDE is weakly complete. That's not so hard to show, but I won't go into this. Now let us denote solutions by find t of x. And then the following is true. For each q, which is strictly smaller than mu plus 2 mu being this number, there exist numbers c1 and c2 such that this moment estimate is satisfied, and that's exactly what we need in order to then apply Kolmogorov's continuity theorem to get the existence of continuous modification. Okay, why is this true? Okay, well, this I won't go into. So what you do is you just define zt to be the difference, modulus of the difference to the power mu plus 2, mu being this number. Then you apply Ito's formula, you see that you exactly need this kind of condition. You plug in this estimate, and then what you end up with is an inequality given here. And again, we are in business using our stochastic Cronwell lemma. This is a continuous local multigrid starting off at 0. And this is exactly like the form before. This is a constant which corresponds to our h on the previous transparency. So we use the stochastic Cronwell lemma, which provides us with an explicit estimate on the rth moment, say, of the soup of this process here, and you plug this in, you get this one. So you see, this P in the stochastic Cronwall lemma had to be slightly smaller than 1, so that's why this Q is slightly smaller than the U plus 2. So you get from this, you get this estimate, and then of course from this you can apply Kolmogov's continuity theorem, at least if Q is sufficiently large. So if mu is larger than D minus 2, then you can choose Q larger than D, and then you're in business. You can apply Kolmogov's continuity theorem, giving you a continuous modification of the process. Okay, that's not bad, but of course we would like to do better because it's a bit annoying that we have this constant k in here. We would actually like to allow the k to grow when x or y become large. So we don't want a global one-sided Lipschitz condition, but just a local. So let's see whether this is possible. So the next lemma is just a generalization of this one, and it's proved very similarly. Okay, so this is almost the same lemma, the same left-hand side here, but we have replaced the constant k by a function f of the maximum of these two norms here. And then again, for each q in that range, and each epsilon positive and b some number defined here, we again get an upper bound for the expected value of the qth moment of the supremum of the difference here, which is given by this one here. And you see if f is equal to a constant k, then essentially we get the old lemma from the previous transparency. But this is a bit more general, and to prove this first inequality again requires the stochastic Cronwall lemma, which is now slightly more general than the one which I showed you before. And that's actually not in the paper with Max and Vanessa, but it's also easy to prove. So this is again application of some appropriate stochastic Cronwall lemma of the same type. And now, what is not so nice about this is that you estimate something which you would like to estimate. I mean, we have to show that this is finite. So we have something here, you have x minus y to the power q. And then all we really need to know is that this is finite and it's actually locally bounded if x and y are bounded. But this still concerns the two-point motion, so it's not so easy probably to estimate this. But what you can do is now f is non-decreasing, so we can make this larger by taking the sum of f of the first term plus f of the second term. That gives us a sum in the exponent, so it gives us a product of two terms, and then we just apply Cauchy-Schwarz inequality, and that gives us this one here. By Cauchy-Schwarz we get this, and this now is only something depending on the one-point motion. This has nothing to do with two-point motion. But again, maybe I should explain what this means here. So actually in Shumei-Lee's thesis, and then also in the paper in PTRF, which appeared in 1994, she suggests, she came up with a very similar kind of estimate. It was not exactly the same, but similar. So what one can do is one can apply Jensen's inequality by just multiplying this by t times 1 over t, and take this integral outside of the expected value here by Jensen's inequality, and then you just need to estimate exponential moments of the solution. F applied to the solution, and that's usually easy to obtain. Okay. Okay, so the following corollary. I mean, this is true for any mu, but if mu happens to be larger than d minus 2, and if the last expectation, if this expression here is actually locally bounded in Z, then the ST is strongly complete because we can again apply Kolmogorov's continuity theorem, providing us with a continuous version of the solution. And I hope you appreciate this. Is very easy, very simple. I mean, I almost gave you a complete proof of everything, and you can already recover basically all the results on strong completeness, which I know of in the literature. So, in particular, the following one. So here, what this means is the following. So assume that we have drift B and a noise which satisfies either this property or the next one, or the one down here. Then I'm claiming that if you define f in this way with an arbitrary beta, then with this f, this expected value on the right-hand side in the previous transparency is finite. So you can allow the Lipschitz constant, which is actually not a constant, but this f to increase like written on the next transparency, and you still get strong completeness. Okay. So maybe you should look at the second line first, because this recovers results which are known from the literature. So here we assume that separately this term is linearly bounded and this term is linearly bounded, and then you can choose f to grow like square of log. Maybe you should observe that here there's no square here, so if you really want to compare this with the Lipschitz condition, you should take the square root out of this. Okay, so this means that the local Lipschitz condition can grow like log in case we have a linear bound on this one and on this one, and this is exactly corollary, which is written in Chaumet's thesis and in her paper in PDRF. She had slightly more restrictive assumptions, assuming that the vector fields were differential, which I don't assume here. So this is just locally Lipschitz. Not even locally Lipschitz, just one-sided. Well, in this case, it's actually two-sided Lipschitz. Well, it's not two-sided locally Lipschitz, just two-sided linear bound, if you want. Okay, then there's another paper which I should mention by Fang, Imkeller, and Tusheng Zhang from 2007 in the Annals of Probability, where they essentially also proved the same result with the log here, exactly like this one here, but they have even stronger assumptions, but they have a completely different proof. Okay, then maybe you should first look at the first line. So this is actually a weaker assumption. So here we individually assume that this term and this term both are dominated by this one. Here just the sum is dominated by this, so that's a weaker condition, and indeed we can only prove the result, strong completeness, if f is like this and not with a square. And that's probably best possible because, I mean, here you can really have a strong compensation of these two terms. So this can be very negative and this can be very positive. So this may grow much faster than this one. And so the best control you get on the one-point motion here is that, you know, it has polynomial tails. And if the one-point motion is polynomial tails, then you just get this f. Whereas here, the one-point motion is dominated by a geometric Brownian motion, which has log normal tails, and that's why this function integrates here. One other example is if B and A are bounded, then the one-point solutions have Gaussian tails, and then you actually can even take f to be a constant times x squared. So this is all very easy to verify. Okay. It may be of interest also to, well, not insist that you have a globally continuous map, but just have this thing locally. So if we just assume this condition with mu larger than d minus 2 to hold locally with kn increasing to infinity as quickly as you like, then of course you may have explosion. But at least you do have locally a continuous modification up to explosion. Okay. Now, stochastic semiflows. So stochastic semiflow is something a bit more restrictive. So we do not just want that we have continuous dependence on the initial condition, but we even want the solutions to form a stochastic semiflow. Of course, we cannot expect a stochastic flow of homomorphisms because even in the deterministic case, you know, this condition here allows for solutions to coalesce, and I mean B could be something like minus x cubed or so. So the solutions are not at all onto or so. So we cannot hope for a stochastic flow of homomorphisms. The best we can hope for is continuous dependence on the two time parameters and the spatial parameter, and to have this usual composition property phi SU is the same as phi ST composed with phi TU if ST and U are ordered. Okay, but to get this we need a slightly stronger condition. So I don't think that we get actually a stochastic semiflow just under this condition, even if this is a constant here, not depending on n. So let's make a very strong assumption for the moment, namely that A and B are even bounded, which is much too strong, of course. But we'll relax that in a minute. And we have this kind of global one-sided Lipschitz condition, but now the mu, okay, in general, mu can be anything greater or equal to 0. Then, first of all, as we know from a previous transparency, the SDE is complete, so solutions do exist forever. And for Q in that interval, and any T positive, there exists a constant C which may depend on T, such that this estimate holds. And I think This is something which you all know. I mean, for example, if you read Cognito's book on stochastic flows, I mean, that's what he has to prove somehow to get a continuous modification of the solution in the initial time s, the final time t, and the spatial parameter x. Now, to prove this is fairly straightforward. You see that we change three parameters here, s, t, and x. So you do the usual trick by adding 0 twice and just changing one parameter at a time. You change x to y and leave s and t here. Then we've seen how to estimate this already before. Then you get a term like this with a constant in front. And the other two terms, you have the same x at both locations, and then that's completely standard how to prove this. You do get this q, as Robert said in his talk already. In this time parameters, you get a 1/2 here. And the spatial parameter, you don't get the 1/2. Okay, and from this, of course, you can then again apply Kolmogorov's continuity theorem, provided you know that this holds for sufficiently large q. So if mu is sufficiently large, then you can choose q sufficiently large, and then you have this estimate, and then you get a continuous modification. So, following proposition. So if this inequality holds for some mu which is sufficiently large, namely larger than d plus 2, possibly d is okay, but okay, if you use this estimate, you need d plus 2. Then the SDE actually generates a global semiflow. Well, first of all, from this, you get by Kolmogorov's theorem that it generates a modification which depends continuously on s, t, and x. That doesn't give you the semiflow property yet, but you know that the semiflow property holds true for fixed s, fixed t, and fixed s, fixed t, and fixed x, almost surely, with exceptional sets possibly depending on s, t, and x. But since we know from this that everything's continuous, both sides of the semiflow property equation are continuous, then you get it automatically for every s, t, and x. Okay. So we do get a global semiflow for this one. Okay. Now these assumptions up here are still quite strong. So you have this global one-sided Lipschitz condition, which is a bit of a nuisance. We would like to get rid of that. But that's actually fairly easy. So, well, that's the next one. But what this is saying is if this holds just locally, so with a kn in front, then we cannot guarantee that there is a global semiflow, then the flow might explode, but at least we get a local semiflow. I don't want to define what a local semiflow is, but I think it should be clear what I mean by that. And also, what's quite interesting is this statement here. This is not immediately clear by definition. If you have a local semiflow plus strong completeness, it actually implies that you have a global semiflow, and it's maybe a good idea to actually check these two things separately. We already had some conditions on strong completeness. We have a reasonable condition for a local semiflow here, so if you have both, you actually get a global semiflow. So this is some kind of a topological argument. So strong completeness just means that if you start at time 0, solutions won't explode. But for a global semiflow, you have to show the same thing for every s, and there are uncountably many initial times, so you have to make sure that this is not a problem. But if you have a local semiflow, you get additional continuity properties, so that's okay. You can see that rather easily. Okay, now let me come to, this is the open definition. So we've now seen what is strong completeness and what's weak completeness. So weak completeness, once again, means that global solutions exist, and strong completeness means that that bounded sets, or any set actually, does not explode. You have non-blow-up of every set, and in the other case, you just have non-blow-up of sets with a single point. And of course, you can somehow interpolate between these two concepts by requiring that sets of a certain dimension do not explode. And that's actually a concept which seems to go back to David Elworthy from the 80s, I guess, and Shumei did a lot of work on that in her thesis. But she only looked at integer values of p, somehow defining strong p completeness as meaning that if you take a p-dimensional submanifold of Euclidean space or of a d-dimensional manifold, then these manifolds should not explode under the flow, obviously. But I mean, there's no reason why one should restrict to integer values of p. So one can also take different dimension concepts, which make sense also for non-integer values. So here are possible definitions. So you can assume either nothing beyond this condition here, or you can already assume that the SDE has a locally continuous modification phi. By the way, I should mention that these phi, I mean, if there's a usual phi, it really just stands for a solution, and these var phi's always stands for a modification with particular properties. Or you can even assume that the SDE generates a local semiflow. So that these are three different possible assumptions. And then we call the SDE strongly p-complete for every subset of dimension at most p. There exists a modification phi. Here we already have modifications, but here we haven't. So if there exists a modification phi of the local solution, which restricted to A is continuous and are devalued, so it doesn't explode. And now dimension may stand for different things, either Hausdorff dimension, upper Minkowski dimension, or approximate, or something else. So if you can think of, say, 2 different dimension concepts, then you get 12 possible definitions of strong p-completeness. Okay, and now you can ask, can you provide sufficient conditions on the coefficients of the equation which will guarantee that you have strong p-completeness, for example, in one of these definitions? First of all, let me say that that's also something from Chaumet's PhD thesis. So in the local semiflow case, so if you assume that there's actually a local semiflow, D minus 1 completeness implies E completeness. The reason being, if you take, so what you have to show in order to show this, well, you have to show that if you take a large cube, this cube will not explode in finite time. But if you know that the faces don't explode, then for topological reasons, because we have a local semiflow, it cannot explode at all. You just assume this condition rather than this one. So if you only assume this is not completely clear to me whether that is. So maybe some experts in topology can tell me about this, but it's good enough to just assume this has a locally continuous modification. I'm not quite sure. Okay, now at least one positive result about strong p-completeness. So let p now be not necessarily an integer, just any real number between 0 and d, and assume that for some mu, which is larger than p minus 2, we have this one-sided global Lipschitz condition for that particular mu, but maybe not for larger mu. So, I mean, you might believe that initially that you can always increase the mu by increasing the k, but this is not the case, of course, because there's no reason. I mean, this can have completely different behavior than this one here. So it may well be that from u equal to 1 you have an equation like this, but from u equal to 2 there's no equation like this, even if you increase k by very much. Okay, then the SDE is actually strongly p-complete in the nothing upper Minkowski sense. I'm not sure whether that's true also in the Hausdorff sense, probably not. That's actually not hard to prove, provided you've read the book of Ledoux and Talleyrand. So for q in that interval, we already saw that we get this estimate. If we have an estimate like this, then one can actually apply theorems 11.1 and 11.6 in the book of Ledoux and Talleyrand, probability and balance spaces from 91, to set A of upper Minkowski dimension P. Now this doesn't, I mean, these theorems are designed for upper Minkowski dimension, not for Hausdorff dimension, because they use entropy numbers, number of balls, which you need to cover a set of, the balls have a certain radius, and that fits very well with Minkowski dimension, but not with Hausdorff dimension. Okay, so that's actually a corollary of Ledoux Talleyrand. And you can even get more. So in this case, you can even get bounds on the image of A. So you get actually tail estimates for the image of A under the flow, and that you can definitely not get in the Hausdorff case. On the other hand, I think that the Hausdorff dimension seems to be more appropriate for some reasons than upper Minkowski dimension in this business. Maybe I'll just point out that if you're not so familiar with these dimension concepts, when one case where Hausdorff dimension and upper Minkowski dimension completely disagree is the case if you take, say, a countable set of the unit cube, then that has Hausdorff dimension 0 because it's a countable set, but it has upper Minkowski dimension d. So it's a complete difference between the two concepts. Okay, so that's one question which I don't know the answer to. Probably the answer is no. Now, let me say a few words about strong completeness, different approaches from completeness. So let's again look at this equation here. Assume that B is locally Lipschitz, and now we make a slightly stronger assumption on the driving marginal M. This is Kunita type notation. Basically, it means that the 1 plus delta derivative of the diffusion coefficient are globally bounded. So that's slightly stronger than assuming global Lipschitz. Okay, and now let psi be the flow of the equation without drift. So you just take this equation here without drift. That certainly generates a flow, and that's even differentiable and so on. And then there's something called decomposition of stochastic flows, which is a method which has been used in the literature by several people. So you don't need to look at the details of this, but anyway, you can transform this equation. You can interpret it in a pathwise sense by transforming it, by somehow writing it in this way. So you have the psi here, and once you fix a version of this this flow psi for this equation, then everything is pathwise, even though it looks a bit strange. So you somehow kind of variation of constant technique. So you somehow try to find a formula, find an equation for the thing which you have to plug into here into this flow to get out the solution, and then you see it satisfies this one. And then you just need to analyze this equation and see whether that exists globally or not. And that requires certain estimates on how psi depends on this second argument and how these inverses change and so on. This I've actually done in some joint work with Salah Mohammed in 2003. We did that for delay, stochastic delay equations even. And then you find two sufficient conditions for strong completeness of this one. So this is just in the ODE case, SODE case, not in the delay case. So either you assume that the drift function B increases sublinearly, so that the gamma is smaller than 1. That's okay, then you do get strong completeness, but this is a slightly stronger assumption than assuming linear growth. And also here we have a slightly stronger assumption than global Lipschitz. Or you actually allow linear growth, but then you have to add an additional condition on this one. And that's not so satisfactory because that's not a condition on the coefficients, but actually on the flow. So that may not be so useful. So this is definitely not automatically satisfied. Okay, once you have this, then you might ask, okay, what's quite interesting about this is that you don't need any Lipschitz condition on the B. You just need a growth condition on the B, no Lipschitz condition, but you need slightly more smoothness on the M. And then you're in business. Because here we always needed some kind of Lipschitz condition on the B. And so you might say, okay, maybe the following is true. That's a conjecture, which unfortunately I was hoping to prove it here, but the last 2 weeks were just too short. So it's still a conjecture. I think it's true. So if B has linear growth, and otherwise it's just locally Lipschitz with no control on the Lipschitz constant. So we assume local Lipschitz continuity just knowledge get existing in unique solutions. But the noise now is globally Lipschitz, but that implies strong completeness. I'm still confident that this is true. Actually, one can even hope that something stronger is true if B has linear growth and noise is globally Lipschitz. Images of bounded sets grow at most exponentially, which of course implies strong completeness. But, I mean, now you could say, okay, maybe linear growth can even be weakened by just saying that there is linear growth in the radial component, maybe in the tangential component you can allow anything. But that's definitely not true, and I can show you a counterexample for that. So if B has linear growth in the radial direction, and the noise is still globally Lipschitz, that does not imply strong completeness, even though it certainly implies weak completeness. And even it is true that if B has no radial component at all, just a tangential component, but without any control of the tangential component, and the noise is globally Lipschitz and even bounded, that does not imply strong completeness. And I'll just finish by showing you the idea of an example on the blackboard. over there. So the idea of an example is the following. So we take, again, a two-dimensional example, and we take a large wall, and we define the drift in such a way that it, say, is extremely strong in the tangential direction. Say it goes with a very high speed around the circle, and then if you just increase the drift, the radius just slightly, it goes in the opposite direction again with an extremely large drift, and so it alternates and it's completely chaotic, but okay, that's the drift. There's no radial component in accordance with the what I wrote here. So this is 0, and it's locally Lipschitz, but just locally Lipschitz with no control on the Lipschitz constant. And I would just introduce noise which goes in the radial direction, which is bounded and which is, say, independent if you take distance of distance 1 or something like this. A very weak noise in the radial direction. And then what's going to happen is the following. I mean, if you start with something even just with a small piece here, what will happen? Well, I mean, this will be moved by independent noises here and here. So some part of this image actually will be drawn to this direction, other parts in the other direction, just by chance. So in almost no time, the thing has covered the whole circle here, and then you get these independent noises everywhere. Even though they are small, they're infinitely, well, they're finitely many, but the larger the radius is, the more there are. And within time epsilon, the point here will be moved on the order of square root of epsilon, roughly, in this direction or in the other direction. But there are many of these things, so some will be moved by order of square root of epsilon out here. And well, then we do the ordinals. Then part of the image of this will be here, say, and then again, within basically no time, the thing has spread all over. So the radius has increased by square root of epsilon in time epsilon. And then you make epsilon smaller and smaller as you move out, and then you see the thing starts growing and taking up to infinity in finite time, actually, if you do this correctly. Okay, thank you very much.
It is possible to construct a counterexample similar to the one in the blackboard with a non-degenerate diffusion part.
Yeah.
Yes.
I'm pretty sure it is, but this was just for simplicity. So if you also had a noise in that direction, I mean, I'm not sure whether this particular example works, but I'm sure one can construct something.
I think in most of your theorems, the dependence in X was sort of holder 1, or essentially 1 minus epsilon. But can you have lower holder regularity in the initial condition?
The initial condition.
As in the example on the right, I guess you don't have continuity.
In this example, yeah. I mean, even locally, well, this will certainly be holder as long as this doesn't explode. Yeah, that's for sure. I mean, even almost Lipschitz, I guess. Yeah. So you're asking for conditions which you could actually even
in which you would have lower regularity.
Lower regularity. Possibly, yes, but then you would probably have to even generalize these conditions. Yeah. I'm not quite sure. I haven't thought about that.
There's a question. What? Let's see.